So the operations on functions, it says let f and g be any two functions. A new function can be defined by performing any of the four basic operations on f and on g. So if you look at that first one, that is showing addition. So it says if you take the function of f and g, both of x, they're both in terms of x, that's what this means here. That basically means you're taking f of x and g of x and adding them together. So for example, if f of x is equal to 5x and if g of x is equal to x plus 2, if you were to add f and g of x, that means you're adding f of x plus g of x, which turns into combining like terms. And you get 6x plus 2 because you're taking 5x and you're adding x plus 2, which is 6x plus 2. So it's just polynomial addition. This is stuff that you did back in Algebra 1. There's not a big difference here. The notation certainly is different, but what you're actually doing is stuff that you've done before, which is great. The second problem here, this is what you need to pay attention to, the fact that this second function is in parentheses. Why would this second function be in parentheses? Any thoughts on that? Yeah. Sure, yeah. If there's a coefficient on the outside, and when you subtract, technically there is one. What is it? -1. So if you subtract an entire function from another one, and you saw this in polynomial subtraction back in Algebra 1, if you subtract a polynomial from another polynomial, that negative needs to be distributed in order for that to work. And so same thing happens here. Whatever your first function is, subtract the entire second function, meaning subtract every piece of that second function. So this is going to be 5x minus x, which is 4x, and then -1 times 2 is -2, so you get 4x minus 2 when you subtract it. When you multiply, fg of x would be f of x times g of x, and it just check that over here. And so f of x times x plus 2 is going to be distributed properly. 5x times x is 5x squared. 5x times 2 is 10x. So that's our function when you multiply them. Division works very similarly. However, this one doesn't simplify. If it could be simplified, we would, but it's just 5x divided by x plus 2. Now, we're going to be talking a lot about domains as well today. So that's kind of the thing in addition to that we haven't done a whole lot of. But in terms of the operations themselves, they're not super complex. Some of them will be more complicated than others because we're going to be dealing with a lot of radicals and things like that. But the basics of this is stuff that you did back in Algebra 1, which is great. You can just draw from that knowledge. So it says the domains of the sum, difference, product, and quotient functions consist of the x values that are in the domains of both f and g. So x values in the domains of both f and g. Additionally, the domain of the quotient does not include, so we're talking just quotient here, the domain of the quotient does not include x values for which g of x is equal to 0. So what that means is, we are not including any values of x that make g of x, the denominator here, equal to 0. So basically, what value of x down here makes this function equal to 0? What plus 2 equals 0? What number plus 2 equals 0? -2, yeah. So on this one here, we would say x does not equal -2. Not only does it not equal -2, it cannot equal -2. Does anybody know why? Or actually, get your calculators out for a second. Let's figure this out. So if we use -2, we're saying x cannot equal -2 here. So if you set up a fraction, you go to your math button, scroll over to fraction, open up a fraction, and you can type in 5 times -2 over, oops, it should be -2 in the parentheses, delete, -2 over -2 plus 2. So we're taking x and we're plugging in -2 for x. What happens? What does your calculator tell you when you do that? It says an error, yeah. It says an error divide by 0. Because if the denominator is 0, that doesn't work mathematically. You cannot divide by 0. So in terms of our values of x could be any number so long as it agrees with the function, right? If it's a square root of x can't be a negative number, right? It's got to be 0 or more than 0 if there's the radical with x underneath it. So we have to consider what are the possible values of x? Sometimes it's all real numbers, could be anything, but oftentimes there will be restrictions on what we can have for particular values of x, which we need to consider anytime we're working through these types of problems. So keeping that in mind, let's go ahead and start taking a look at some problems here. So there is a new operation called composition that we will use later in this chapter. So we will be working on some compositions later in the chapter. All right. So the first problem here, example 1, is adding two functions. So it's telling us that f of x is equal to 3 times the square root of x, and that g of x is equal to negative 10 times the square root of x. Find f plus g of x and state the domain, then evaluate the sum when x equals 4. So a couple things we need to do. Or 3 things, actually. We need to add together the two functions to create our new function. We need to state the domain of our new function, and we need to evaluate the function when x is equal to 4. So we're going to take, so step 1, we're going to have f of x plus g of x. F of x is equal to 3 times the square root of x. And then we're going to add to that negative 10 times the square root of x. What's the result? I'm going to use some stuff that we did earlier in chapter 5 in terms of that similar radical business that we dealt with earlier. So what do we get? So we're adding them together, right? So if you have 3, yeah. So if you have 3 root x's here and you have negative 10 root x's here, how many root x's do you have? Negative 7, yeah. So this is going to be negative 7 root x. That's what happens when we add them together. So we talked about radical addition earlier in this chapter, and radical addition works basically like terms. If you've got like terms, then you can add together the coefficients. Like terms are root x, coefficients are 3 and negative 10. Put them together, keep your like term or your like radical, and that's it. So we get negative 7 root x. That's the first part. Next, we need to talk about the domain of this function. So the domain here, what possible values of x work with this function? The radical is the clue here. And specifically the fact that we have an even index value, it's a square root. What types of numbers work for x? Okay. In terms of perfect squares, sure. We can still, we can find the square root of 2 if we wanted to. It's just an irrational number, but it is possible to find the square root of 2. Yeah, anything that's not negative works here because negative radicals under an index that is even don't work. The values in the radicand must be 0 or greater in order for them to be evaluated when the index is an even number. Square roots, fourth roots, etc. So we're going to get x is greater than or equal to 0. That is our domain. Negative numbers cannot work for this particular function because we would not get real number solutions. We could get imaginary solutions here just fine by using negative values, but we're not dealing with negative radicals or imaginary values right now. So there it is. And that is because x is under a radical with an even index. If the index was odd, if it was like negative 7 times the cube root of x, then the domain would be all real numbers. Because you can cube root a negative number. That's fine. And so the domain's going to change depending on the type of radical we're using. Hopefully, because we talked about this before, right? This is kind of bringing back some stuff with what we dealt with in the first part of the chapter. We took a test on it last week. All right, third part. Evaluate when x equals 4. Evaluate the sum when x equals 4. And that's the answer you gave me, right? And what'd you get for that one? Negative 14, yeah. So if we're evaluating the sum here, I'm going to write this as f plus g of 4. This does not mean f plus g times 4. We're replacing the value of x with 4. This is a substitution. This is not a multiplication. I want everybody to make sure they're understanding it. This is not f plus g times 4. This is f plus g of 4, meaning substitute in 4 for x. So that means we're taking negative 7 times the square root of 4. F plus g of x is negative 7 times the square root of x. F plus g of 4 is negative 7 times the square root of 4. So we're dropping in 4 for x. Square root of 4 is 2. 2 times negative 7. Negative 14. That's it for the first example. So here, just in case you need a reminder, plug in x equals 4. Are these the student companions? Yeah, I bet they are. Trying to think where's good. Maybe over by the bookcase. Thank you. Look at all that. Go ahead and move on. Any questions on the first example? Okay so far? What's that?
3 more blocks.
Oh, this work? Cool. All right. Couple of notes off to the side here. Let's go with, so even roots. So if n is even, then everything under here must be greater than or equal to 0, no matter what. So if we're talking about domains, if you're trying to figure out values for the domain, it's all based on, if you're talking about radicals anyway, it's all based on what's under the radical if it's an even root value. If it's an odd root value, it's going to be all real numbers. That's fine. But if it's an even index, even root value, we're talking about greater than or equal to 0 because you can't square root a 4th root or 6th root any negative value. That doesn't work. Okay. Let's keep going. Flip it on over. Next, we're talking about some subtraction. So this one's going to function very similarly to the one we just did. We just need to make sure that that second function here ends up in a set of parentheses so we can distribute the negative to combine those like terms. So our first step is going to be f of x minus g of x, which will look like 3x cubed minus 2x squared plus 5 minus second function, all in parentheses, x cubed minus 3x squared plus 4x minus 2. You can write out the next step having this distributed. I'm not going to do that. I'm just going to make sure I apply the negative to everything inside of here. So 3x cubed minus x cubed would be 2x cubed. Negative 2x squared minus negative 3x squared would be negative 2 plus 3, which is 1. So that would just be plus x squared. There isn't an x here, so this will be minus 4x. And then we're taking 5 and subtracting negative 2, which is the same as adding 2. So that'll be minus 4x plus 7. So this is our function f minus g of x. Does it look like there's any restrictions on values for x in this one, for the domain? Is there anything that isn't going to work for a value of x? Like, could we plug in negative 2004 and still get a number for y? Yeah. Could we plug in 17.6 for x and still get a number for y? Yeah. So for 2, our domain here, domain is going to be all real numbers. So domain, all real numbers. Doesn't matter what x is, we'll get some value of y. There's no restrictions on that one. For number 3, we're going to evaluate the difference when x is equal to -2. Now, there's a couple ways to go about doing this, and I'm going to remind you of one of the ways that you learned how to do this that we did back in chapter 3, I want to say. But let's go ahead and do it the long way first, and then I'll remind you of a way that maybe is a little bit quicker, unless you remember the other way, which would be kind of cool. So here we go. This is going to be f minus g of -2. So this time we're substituting in -2 for x into our answer to the function subtraction here. So that's going to equal 2 times -2 cubed plus -2 squared minus 4 times -2 plus 7. Let's see. -2 cubed is -8. -8 times -2 is -16. So that's -16. -2 squared is +4 plus 4. -4 times -2 is +8 plus 8, and then plus 7. And let's see. 8 plus 7 is 15. -16 plus 15 is -1 plus 4 more is +3. So 3. Is our answer for that one. Use a calculator if you want to. Now, does anybody remember another way to do this? From chapter 3. Anybody remember what we did in chapter 3? Okay. I'm going to set it up, and I'm going to see if this looks familiar for evaluating here. That was familiar? What did we call this? This is synthetic division, yeah. Remember, we can evaluate a value of x with a function. Thank you, Alex. You can evaluate the value of x with a function by using synthetic division. Plus, it'll also tell you if what you're dividing by is a factor of that original function anyway, which isn't really relevant here, but we can find that out. So, process for synthetic division. Bring down the first term all the way down here. Anybody remember what to do next? Multiply, all right, 2 times -2. That's -4. What do we do with the 1 and the -4? We add them, good, which would be -3. And then we repeat the process. -3 times -2 is 6. 6 plus -4 is 2. 2 times 2 is -4. 7 plus -4 is 3, which is our answer. The remainder of synthetic division is equivalent to evaluating for a certain value of x. And if you remember what we're dealing with here as well, this is the remainder. This is our constant. This is our linear. And this is our quadratic. So basically what we just did is we divided this function here by x plus 2. If you go back to synthetic division. And we found out that dividing this by x plus 2 is not a factor of it because there's a remainder. So just a quick reminder on that chapter 3 stuff. So either way here is fine, by the way. I don't care which method you use. I just want to remind you that this is an option for evaluating a polynomial function for a certain value. So that's something you can do. It's not something you have to do. Okay. Example 3, multiplication of two functions. Let's keep going. So same thing. Do the multiplication, state the domain, then evaluate when x equals 9. So this time, step number 1, we are looking at f of x times g of x. Which is going to look like x squared times the square root of x. By the way, this is fine. Or if you want to, you can go over here and say x squared times x to the 1/2. You can use rational exponents instead. So this would be equal to x to the 4/2 times x to the 1/2, which would be x to the 5/2. So either one of those is an acceptable answer for the multiplication. So you can write it with a single variable with a rational exponent, or you can write it separately as a squared times a radical. It's up to you. Either way, though, we need to think about our domain. So let's see. That's an even index. That's an even index, right? Both of the index values are even. What does that tell us about the domain? Greater than or equal to 0. Good. So the domain x is greater than or equal to 0. That's our answer there. And then to finish it off, we're going to use 9 for x. So third step is fg of 9. That's going to be our function here or this function here. I'll show it both ways. Plug in 9 for x and evaluate. So a couple ways we can do this. We can say equals 9 squared times the square root of 9, or we could say 9 to the 5/2. Same answer either way. I don't really care which method you use. It's up to you. So over here, that's going to be 9 squared times 3, right? Square root of 9 is 3. 9 squared is what? 81. So 81 times 3? 243. Good. 80 times 3 is 240. 1 times 3 is 3. 240 plus 3 is 243. And then over here, this is the square root of 9, which is 3 to the 5th power. So cancel that out. Like that. Square root of 9 to the 5th power, which is equal to 3 to the 5th power. What's 3 to the 5th power? $243. Yeah. So either way, I mean, it better be, because we said it was the same problem. So either way, 243 for that thing. Questions so far? We've done addition, subtraction, multiplication. Division is where I think it starts to get a bit more challenging. If you feel like so far, honestly, the hardest part of this is probably going to be figuring out the domain. Because adding the functions, plugging in for a value, we all know how to do that really well. thinking about what possible values of X, I think that's going to be the hardest part of these problems. All right, flip it over. Here we go. Division. So now we are taking a look here at 6x is f of x, g of x is x to the 3/4 power. Now we're going to be dividing f by g of x. So part one, we're going to do the domain. We'll plug in for when x is 16 as well. Step one, we're going to take f of x, and we're going to divide that by g of x. So that's going to end up being 6x divided by x to the 3/4 power. What do we do now? What's that? I like the subtraction word. Do we have the same variable in the numerator and denominator? Both x, right? What can we do with exponents if you have the same exponent on the numerator and denominator? What's the exponent rule there? We have it in some previous notes. Like off to the side here, let's say I've got x to the 7th power divided by x cubed. What's the answer to that? X to the 4th? Why is that? Subtract the exponent. There you go. So I'm going to write x, by the way, what would the exponent be here with this x? If there isn't one, but what would it be? It would be 1, which would be 4/4. All right, so I'm going to write x to the 4/4 power. Because x to the 1st power is the same thing, but I'm just making a common denominator, so that'll make it easier to subtract. 4 minus 3 is 1, so that's going to give us 6x to the 1/4 power. Or if you want to, 6 times the 4th root of x. Now, we have to be a little bit more careful this time about our domain. We have to consider both the beginning and the end for possible values of x. We have to consider two things here, because with division, we cannot have a denominator equal to 0. So we have to consider that here. We also have to consider the results of an even index value and what x can and cannot be as well. So there's two things here that are causing restrictions on our value of x. Is everybody okay with that so far? Like, just conceptually, we're not figuring out what x is yet. I'm just saying we have to look in both places, because we said on the first page of notes here, where we have division, if you're dividing and you have a variable on the denominator, that variable, whatever the denominator is, cannot equal 0 because you can't divide by 0. And so even before you simplify it, you have to consider that. So what we're looking at right now is division with a variable on the denominator. So the denominator itself cannot equal 0. And because we have an even index value over here, we have to consider that with our value of x under the radical as well. So there's two restrictions happening here with our domain. The first restriction happens with the denominator, so 2. Let's say domain. We have to think about this right here. So I'm going to bring this down, and I'm going to say x to the 3/4 cannot equal 0. Yeah.
You said x adds 0, then 0 over 0.
Right.
Would that be allowed?
No. Nope. 0 divided by 0 is also an error. If you don't have something, you can't split it into 0 parts. Like division talks about splitting things into certain parts, right? If you don't have anything, there's nothing to split it into parts anyway. And if you have something, you can't split it into 0 parts because you have something. But if you don't have something, you don't have any parts to split it into in the first place. And so you can't take 0 and split it into 0 parts because you never had anything to begin with. And you can't take a number 4 and split it into 0 parts because you have something. And so dividing by 0, and again, if you go back here, we take 0 divided by 0, it's going to give you that same error. So 0 divided by 1 is 0, but 0 divided by 0 also doesn't work. So basically what we're trying to figure out here is what value of x makes x to the 3/4 equal 0. It would be 0, right? It would just be 0. Like this would equal 0 to make the denominator equal to 0. So we're just dealing with the denominator right now. So what value of x? So basically we're looking at, okay, the 4th root of x cubed equals 0. What value of x makes this equal to 0? There's 0. Yeah. So that means that x cannot equal 0. That's part of the domain. And this is because of the denominator. Now, the other thing in the domain we have to consider is here. And so we'll bring that down and we'll write that as x is greater than or equal to 0. But we just said that x cannot equal 0. So those two things are at odds with each other. Because this includes 0 and that doesn't. But we showed for sure that you cannot have x equal 0. So that basically just means we need to get rid of the or equal to version part of this. So x has to be greater than 0 no matter what. To satisfy both of these at the same time, x has to be more than 0. It could be 0.00001. That's fine. It just can't be equal to 0. It also cannot be negative. So that means our domain is x is greater than 0. That's the domain. We have to consider both the radical and the denominator. And then come up with the thing that actually works with both at the same time. Everybody okay with that? Like I said, figuring out the domain of these problems is probably the hardest part. Doing the division, doing the subtraction, the multiplication, the addition, all that stuff, not too bad. You've done that work before. Evaluating, you've done that work before. That's not too bad either. It's this here, it's the domain that's going to be tricky. Now, if you want to, you can type these functions into your graphing calculator and then look at what values of x are possible. And that could be a helpful thing. We're actually going to take a look at that on the last couple examples. So step 3, let's go ahead and plug in here. We're using 16 for x. So we're saying f divided by g of 16. F divided by g is here or here, either way. I'm going to use the radical one this time. So this will be 6 times the 4th root of 16. What's the 4th root of 16? 2. What's 2 times 6? 12. All right. So again, the evaluation part, not bad. And that's certainly greater than 0, so that works just fine with our domain. All right. Any questions? We've done an example of each type. We've added, subtracted, multiplied, divided. Anybody have any burning questions right now? So example 5, there's a few things we're going to do here. We're going to take our f of x and our g of x, and it says to use a graphing calculator to find f plus g of x, f minus g of x, f times g of x, and f divided by g of x. When x equals 2. So all we need to do here is evaluate. We don't have to write out step 1 from up here. We don't need to write out the domain step 2. We're just doing step 3 for each of our functions here. So the way we can do this is if you want to make a composition, like if you want to combine them together, you can, but you don't have to. You can just write it out. So let's see. First one, the addition. this will be f of x or f plus g of x. So we'll say f plus g of, not x, f plus g of 2, because we're using 2. We're evaluating for 2. So all you have to do here is take your two functions, square root of x, and plug in 2 for x, and then add to that square root of 9 minus 2 squared, and then solve that. And if you need to, it says in the directions here, round your answers to the nearest hundredth. So what I'd like you to do is just work through those 4 problems, type them into your calculators, figure out the answers, round to the nearest hundredth if you need to. And we'll take a look in, I'm just going to give you 2 minutes to do this. See what you can do in 2 minutes if you can get all 4 of those done. Yeah. Oh, sure. Yeah. You're welcome. And in order to evaluate these, you will need a calculator. So these are not mental math type problems here. So there they are. Make sure you're getting those answers on your calculator screen. And then if you got any questions, if something's not matching up, let me know. So those are the answers to those 4 problems when x equals 2 for each of our different types of operations with functions. All right. Any questions before we look at our final problem? All good? Okay, flip it over. Look at the last one. So this one's a word problem. We get to talk about the lifespan of a rhinoceros. I don't know why, but that's what it is. So here we go. Example 6, solving a real life problem. So for a white rhinoceros, heart rate R in beats per minute. So R of M, that would be rate of the heart in beats per minute. And the lifespan S in minutes as well. So think about how long something lives and think about that in minutes. It's a lot of minutes, right? This can make the problem easy. So the fact that both things are in terms of minutes, that's going to make this problem a lot easier. Because if it was in terms of years, we would have to then, divide by 365 to get days, and then divide by 24 again to get hours, and then divide by 60 again to get minutes. And so we'd have to be doing a lot of unit conversion. So having both of these in terms of minutes is really nice. So we're talking about the heart rate in terms of minutes and the lifespan in terms of minutes that are related to body mass, M, in kilograms by the function So the heart rate is 241 M. Oh, sorry, M is not the minute. Sorry, M is the mass in kilograms. So heart rate per in terms of kilograms, mass in kilograms is what we're talking about. Beats per minute related to how heavy the elephant is in white rhino is in kilograms. So the function that is modeled to figure out heart rate beats per minute for a particular rhinoceros with a certain weight in kilograms is modeled by 241 M to the negative 0.25 power. And in terms of the lifespan in number of minutes, that's why it's a lot of minutes, which is why this is written in scientific notation, because it's going to be a lot of minutes. In terms of the mass, so lifespan in minutes in terms of mass is equal to 6 times 10 to the 6th power multiplied by the mass taken to the 0.2 power of that. So what we have to do is figure out RSM. So this would be the two functions, beats per minute, multiplied by lifespan in minutes of the mass in kilograms. But this is the multiplication kind that we were looking at before. So what we're doing here is we're taking R of M, and we're multiplying that by S of M, which is going to be those two functions multiplied together. That's what we're taking a look at. So that will give us 241 M to the negative 0.25 power multiplied by 6 times 10 to the 6th power multiplied by M to the 0.2 power. Now, I don't know about you, but I feel like we're looking at the same variable here and here. Those both relate to mass in kilograms. Everybody cool with that? And is everybody also okay with the fact that with multiplication, I'm going to put a dot in between the 241 and the M and a dot in between that parenthesis and that M? Is everybody comfortable with the commutative property of multiplication, where it doesn't matter what order you multiply and you're going to get the same answer, right? 3 times 4 is 4 times 3. Yeah. So I'm going to rearrange some stuff here to make things a little bit more navigatable, I guess. Navigable would be the right word for that. So we're going to get 241 times 6 times 10 to the 6th power times M to the negative 0.25 times M to the 0.2. So I'm just rearranging things to match our regular values with regular values and then variables with variables. Now, I'm not very interested in multiplying this out by hand, the 241 times 6 times 10 to the 6th power. So I'm just going to multiply that on my calculator. So 241 times, parentheses, 6 times 10 to the power of 6. There it is. 1, 2, 3, so 6 zeros. So 1446 and 6 zeros. 1446 and 1, 2, 3, 4, 5, 6 zeros. So that'd be 1,446,000,000. That's the number we're looking at there. And then we need to add the exponents here because we have the same base value. What's negative 0.25 plus negative plus 0.2? Negative 0.25 plus 0.2. Yeah, negative 500ths or negative 0.05. Nice. So that's our value. Now, that's part A. Okay, so what does that mean? What does this number represent? That's what this is asking. Explain what this represents. What did we just do? Any thoughts? We might wrap up this question. We'll wrap up this question tomorrow. I want you to think about what this means. What in the world does that mean? I'll post the notes online, but I'm going to leave B blank, and we'll talk about that tomorrow. You do have an assignment for this, but think about what this large number means in relation to the mass in kilograms of a white rhino. And we'll come back tomorrow and I'll ask that question again. Leave you on a cliffhanger today.